Acceleration is defined to be, or at least average acceleration is defined to be the rate at which we are changing velocity. So our average acceleration is equal to our change in velocity over time, or v minus v naught over t. So there's at the top our change in velocity. We went from some starting velocity to another, and we did that over a certain period of time. So how quickly we're changing velocity is what acceleration is. Because acceleration is a vector, it's very important to pay attention to direction. So let's make a reference point here of 0, and over on this end is positive, and this end is negative. Okay. Maybe an easy example here. If our velocity is positive, so we're headed towards the positive direction, but our acceleration is negative, then that would mean we're slowing down, okay, if they're in opposite directions. If instead we take our acceleration, so instead of this, our acceleration is in the same direction as our velocity, we would be speeding up. Okay. The less obvious one, and the one that's a little harder to think about, might be something like this. If I have a velocity that is negative, and I also have an acceleration that is negative, I would still be speeding up because they're in the same direction. I'm just speeding up in the negative direction. Okay. If we take the opposite example, I could have a negative velocity and a positive acceleration. Since this is going towards the negative direction, this is going towards the positive, that's opposite direction, so it would be slowing down. So even though it has a positive acceleration, it's slowing down because my velocity is negative. So to decide what an object is doing, you have to pay close attention to which direction both velocity and acceleration are in both of those examples, and in all the examples you'll do. So what we want to develop now are our kinematic equations. These are going to be a set of equations that are going to be very useful to us in solving problems. So there's going to be a certain mathematical process that we go through to get these. I'm not too concerned about that you understand the process, but you will need to know the equations and be able to manipulate them. So the first equation, kind of very simple, comes from our last equation where we had acceleration equals velocity minus v naught over t. And we're just simply going to rearrange this equation. So I'm going to multiply both sides by t. So I get at equals v minus v naught. And then solve for v. So v equals v naught plus at. And that is the first of our useful kinematic equations. So this equation could be used to tell you, how fast something is going after a period of acceleration, as long as you know how fast it started. So a useful equation there. For the next equation, we're going to kind of start where we left off with velocity equals v naught plus at. And we're going to do kind of some funky math here, but you'll see what it comes out to in the end, and something useful. First thing I'm going to do is add a v naught to both sides. Since I'm doing it to both sides of the equation, it doesn't really change the equation. So v plus v naught equals v naught plus v naught, which would be 2v naught plus at. And then I'm going to divide both sides by 2. So I have v plus v naught over 2. Well, 2 divided by 2 is just 1, so v naught plus at over 2. Now we're going to kind of step aside here for just a minute and define another quantity here. Our average velocity, so when you write v with the little bar above it, that can mean average. So our average velocity we could find by taking v plus v naught divided by 2. So that's an equation you could use to find the average velocity. Well, notice that quantity shows up here. So we're going to plug in average velocity over here on the left side equals v naught plus, and I'm going to write this as 1/2 at instead of at divided by 2. Now our average velocity, if you remember from our definition, was the x minus x naught divided by time equals v naught plus 1/2 at. And then I'm going to multiply both sides by t. So I get x minus x naught equals v naught t plus 1/2 at squared. And then I'm going to solve for x and say that x equals x naught plus v naught t plus 1/2 at squared. And this is our next sort of useful equation here, t squared. And this is very useful for telling us where something is located, what's its position after a period of acceleration, right? So if we accelerate for some period of time, started with some velocity and started at some location, here's where we're at now. So a very useful equation. For this last equation, we're going to step back to our average velocity real quick and say that average velocity equals x minus x naught over t, and solve for x and say that x equals x naught plus average velocity times time, which is an equation we could use if we wanted to, but not as, we'll find out, a super useful one. We also had our equation v equals v naught plus at. And I'm going to solve for time here. So time would be equal to v minus v naught over a. And you can also recall from our previous equation that we also came up with the equation that v naught was equal to, or v average was equal to v plus v naught divided by 2, so kind of our mathematical average there. And what I'm going to do is take these two equations here and substitute them into this one and see what we end up with. So x equals x naught plus my average velocity, which was v plus v naught divided by 2, times my time, which was v minus v naught over a. And so that's kind of a mess, so let's whittle that down a little bit. So we can say x minus x naught, so move that over there, equals v plus v naught times v minus v naught would give me v squared minus v naught squared over 2a. And so we're going to multiply by 2a, so we'll have 2a times x minus x naught equals v squared minus v naught squared. And I'm going to kind of flip things around here and say that v squared would be equal to v naught squared plus 2a x minus x naught. And that is our final kinematic equation there. So this one's very useful for finding out, how fast something has gone. If we know how fast it started, its acceleration, and its change in position, or, again, any of the variables in here. And this is a great equation, especially if you don't know time, right? You'll notice that our other two equations had time in it. This one does not. So if you're not given time in a problem, this might be a good equation to use. So just to kind of sum things up here, the three important kinematic equations that you're going to be using a lot are v equals v naught plus at, x equals x naught plus v naught t plus 1/2 at squared, and finally v squared equals v naught squared plus 2a x minus x naught. Your book might give you another one. There were some other ones that we came up in there to find these that may be useful in certain situations, but really any kinematic problem that you come across can be solved using just these three equations.